Hello and welcome back to episode 2 of C programming. In the first episode, we looked at variables, how do we store data inside a C program, what are data types, and a few basics to get us started. So here we are going to look at a different view of the C program. So in this episode today, we're going to look at the secret life of a C program. Yes, you heard it right. Have you ever written a piece of C code, hit the run button, and wondered what actually happens next? It often feels like magic, right? But behind that magic is a remarkable journey. A journey your program takes from being plain text on your screen to becoming a living, running process inside your computer. So let's take the most familiar example, the famous Hello World program. You have seen this before, but how does a computer that understands only ones and zeros take these English-like words and make them appear on your screen? To understand that, we have to start at the very beginning of your program's life, on what I like to call as the digital assembly line. So let's look at what a digital assembly line is. Your source code, the text you write, goes through 4 stages of transformation before it becomes something that the machine can actually execute. The first step is the preprocessor step. This is the first stop. The preprocessor scans your code for lines that start with a hash, like hash includes standard io.h. It literally pulls in the contents of these header files and pastes them directly into your code. It's pre-processing. It has not yet started processing your program. By the time this step finishes, your file is much bigger than what you originally typed because you included so many header files. So next step is the compiler. The compiler takes this expanded file, translates it into assembly language. So assembly language is a low-level representation that is closer to what the CPU can understand. It is still not the exact zeros and ones that the CPU can understand, but it is closer. It also checks your code for errors and applies some optimizations. The third step is the assembler step. Now the assembler converts that assembly code into pure machine instructions, purely ones and zeros. These instructions are placed into a file called an object file, .obj, which is still incomplete, but now fully machine readable. The machine can read your code, but it is still incomplete. It is missing something. That step is the linker step. Step number 4 is the linker. Finally, the linker steps in. If you used functions like printf and scanf, the linker will find the compiled machine code for these functions. They are stored in standard libraries. It will go and find these functions for you, stitch everything together into a final executable. This is the moment your program becomes a real .exe or a .out file, something that you can run. So the factory work is complete, it's all assembled, but your program isn't alive yet. It is just sitting on your hard drive. You have a .exe file or a .out file. It is just sitting there. So then comes the loader, which brings your program to life. The moment you double click your program, another crucial player enters the system. That guy is the loader. Think of the loader as a moving crew. Its job is to take your executable from the disk and carefully place it into your RAM, your computer's active memory. Only after this move is complete, your program is ready to run. But the loader doesn't just dump everything into memory at a random location. It doesn't do that. It sets up a beautifully organized layout like a house with different rooms, each designed for a very specific purpose. So let's take a tour of this house, whatever the loader is laying out for us. The memory house. Your program's memory layout is divided into distinct segments, and each one has a very specific role. There is an area called the text segment, the library. This is where all the machine code instructions live. The real executable part of your program is the text segment. It's usually marked read only, so your program doesn't accidentally overwrite itself with its instructions. Then comes the data segment. This is like the pantry, the kitchen. This is where you do your cooking in your house. So along with the text segment, there is a place called the data segment, the pantry. This room contains all the global or static variables that you gave, where you assigned a value, and basically where you set up your variables. This comes pre-stocked. So if you go into your kitchen, it is ready with ingredients that you can use for your cooking. So the initialized data segment, the pantry, this comes pre-stocked. When the program starts, it will hold all your initialized values like global and static variables. Then comes the BSS, or the uninitialized data segment. This is the empty storage room. In your home, you have a storage room where you dump a lot of everything that you use. So this is that. If you declared a global variable but you did not assign any value, this is going to be dumped here in the storage room, the BSS, the uninitialized data segment. Before the program starts, the operating system clears this entire room. Every time the storage room is cleared, sets everything to 0, and then it starts. There is something more. The dynamic duo, the stack and the heap. So what are these? So far, the rooms we visited are all static. There is a storage room, there is a pantry, a kitchen, there is a library where all your code is sitting. Now we reach the truly dynamic part of the house, the ones that grow and shrink and constantly change while your program runs. The first one is the stack. This is the organized clean desk. Whenever you call a function, the stack creates a sheet of paper, calls it a stack frame, which will contain the function's local variables, function parameters, return information, whatever the function needs for it to work. It's a function. So this is the sheet of paper called a stack frame. So when the function finishes, that sheet is automatically thrown away. It's very fast, efficient, self-cleaning. The house is clean. The function is given a special area in the stack. It's called a sheet of paper, and it's called a stack frame. So it has a fixed size. Overflow it and you'll get a stack overflow. So that is the stack. So in the dynamic duo, the dynamic part of the house, there are two areas: the stack, which we talked about, and then the heap. The heap is the expanding workshop. When your program needs memory during runtime and you don't know the size in advance, you request space from the heap. You use malloc, memory allocate. Malloc is a function which will allocate some space for you to do things. Unlike the stack is a sheet of paper you throw away, right, when the function completes. The heap doesn't clean up after you. The heap is just there. If you take memory and forget to return it back with a special method called free, the memory stays occupied, and that becomes a memory leak. So you have to use the heap very responsibly. Heap is what you use to dynamically get some memory and do something with it. So stack versus the heap, what should we use? What are the differences? The stack is short term, it is automatic, very fast. You are unaware that a stack exists. Whenever you invoke or you create a function and invoke it, that particular function will be given a stack frame, a sheet where it will keep writing things. It is automatic, and once the method is complete, it will throw away that sheet. The heap is more long term, it just stays there. It is flexible, manually managed, but the heap is available. So when you as the program ask for some memory, it comes from the heap. But when a function asks something automatically without you knowing about it, that goes into the stack. So those are the small differences. I mean, don't take everything too literally. It's just to give you an idea of how the stack and heap works. You can look up the details of how all of this memory organization works. But it's important to understand that there are dynamic memory structures available for our use. So understanding the difference between these two regions is one of the keys to avoiding a classic issue that C programmers face, which is the out of memory exception, or it can also be unauthorized access exception. So just to recap, I'll keep this episode short. This is about the life story of a program you wrote, the Hello World program. So to put it together, your C program starts as plain text. It passes through 4 stages of assembly line: preprocessor, compiler, assembler, linker. It gets loaded by the loader into RAM. It moves into a structured house with text segment, data segment, stack, and heap. Finally, it comes alive as the CPU begins executing the instructions one by one. So from a simple Hello World program to a complex memory layout, the journey is anything but simple. It's not magic, it's beautifully designed process. And now that you know how the house is organized, the real question is, how can you use this knowledge to design smarter, faster, more efficient programs? Something to keep in mind as we move deeper into C. So that brings us to the close of this episode. We understood how a C program becomes a living executing process in memory, and we understood the different memory organization and layout of the C program, which are all important as we go into actually building complex C programs. So that's about it. So if you like the episode, do like it. If you have some comments, drop some comments and questions below. Do subscribe and come back for more. Thank you for watching.